This is a nice long review paper on flash droughts, which is a nice new hot topic. Includes a big team of international scientists. Our own superstar from India, Vimal Mishra, is on it as well. And he's been writing a lot about droughts, and he has produced drought indices for India and so on as well. As I said, it's a long paper, but I'm going to make it a brief review, even though it'll be longer than 30 minutes. You know, and the paper has incredible number of really nice references that you need to follow up, as well as the paper itself if you want to get more details. My idea is to learn enough myself, learn well, to give you a brief introduction. I learn for my own interest, as well as my interest in producing early warnings for everything, including flash droughts, let's say. And there's been some complaint from a colleague saying, oh, how can you do so many things? Well, I do earth system science, so I need to do as many things as possible to cover the range. And just because somebody does lesser topics than me doesn't mean they're doing it better, right? So quality of the work matters a lot. So with that little complaint, let's look at flash drought, a state of the science review. Review articles are always long, but they are useful. In the 2 decades since the advent of the term flash drought, considerable research has been directed toward the topic. Within the scientific community, we have actively forged a new paradigm that has avoided a chaotic evolution of conventional drought, but instead recognizes that flash droughts have distinct dynamics and particularly impacts. So when you introduce a new term like flash drought, you have to say why it's different than a drought, even though there are many different definitions of the drought itself. And you have to say if it is also different in terms of its impacts, because then forecasting, the scale of the forecast, the time lead with which you have to forecast, all depend on the impacts. We have moved beyond the initial debate over the definition of flash drought to a centralized focus on the triad of rapid onset, drought development, and associated impacts. The refinement toward this general set of principles has led to significant progress in determining key variables for monitoring flash drought development, identifying notable case studies, and compiling fundamental physical characteristics of flash drought. However, critical focus areas still remain, including advancing our knowledge on the atmospheric and oceanic drivers of flash drought, developing flash drought specific detection indices and monitoring systems tailored to practitioners, improving subseasonal to seasonal predictions of these events, constraining uncertainty in flash drought and impact projections, and using social science to further our understanding of impacts, particularly with regard to sectors that lie outside our traditional hydroclimatological focus, such as wildfire management and food security monitoring. Researchers and stakeholders working together on these critical topics will assure society is resilient to flash drought in a changing climate. So a lot of information there, but you get the idea that subseasonal to seasonal forecasts, I have a full course on it on my channel. 1 to 3 days, 3 to 10 days, weeks 2 to 4, subseasonal, and then you have to combine with seasonal, which goes up to multiple seasons and so on. And impact-based indices and impact-based forecasts are now becoming critical as we, now we have marine heat waves, we have flash drought. So what do they mean in terms of impacts, and why is it important to predict them, understand them, and so on and so forth. So just to read off a few more things, I will jump ahead. While drought itself has been simply defined as insufficient water to meet needs, it is challenging to classify different types of droughts due to the diversity of compound and cascading causes and effects. Traditionally, drought has been classified as meteorological, hydrological, agricultural, ecological, and socio-economic, based on the duration of the abnormally dry weather, which is the most important characteristic of drought, location within the water cycle of the drought impacts, like stream flow versus soil moisture, let's say, and their complexity. Flash droughts are a subset of all drought types that are characterized by unusually rapid intensification, either to begin a drought or to exacerbate an existing drought. We'll see an example. The earliest mention of flash drought-like events is the Sukhoi, I don't know how it's pronounced, Russian word, which was first noted in the southern plains of Russia and later examined in the plains of North America. These events were characterized by hot and dry air masses with extended precipitation deficits that led to rapid plant stress and wilting. So, warm air, dry air is very thirsty, vapor pressure deficit goes up. So, when leaves open for capturing CO2 for photosynthesis, wilting and stress becomes very quick when you have droughts, especially if it develops very quickly. Two studies in the early 1980s were possibly the first to mention rapid drought development and so on. So I will, quit the further details and just look at the Venn diagram. So you have flash rapid onset of drought, which is the critical aspect, the rate of growth, and impacts. Obviously, longevity of the drought leads to impacts and cascades into different sectors: agriculture, water resources, forests, and so on and so forth. And drought itself, which is sufficient drying of the land surface. So the intersection gives you flash drought. Does that help you? Well, at least it helps you to keep the key components in mind, the triad as they call it. And just to jump ahead to an example, this is from evolution over eastern Montana. Which is, we are looking at these regions of the US, Northern Plains region within the United States. In July 2017, soil moisture percentile rank relative to this base period of 1979 to 2017. In July and May to July 2017 precipitation. And the US Drought Monitor started to say things are not doing so well, starting with the intensity in terms of anomaly being dry, already drought, severe drought, extreme drought, exceptional drought scales here. So you can see by August you had exceptional droughts in some spots as well. And you should also see the spatial scales and the heterogeneity in the small region that we are looking at, which tells you the need for maybe region-specific definition, the monitoring, and the prediction skills. And the impacts are going to be different as well. Could be different crops, different forests, and so on and so forth. So here is how it went from April 1, 2017 to October 31, 2017. Soil moisture percentile, it was nice and saturated as you came in. Then it began to drop. Whether this qualifies as flash or not, you have to see. And then you can see there were spikes of rain. So the rain remained below normal in these brown colors for the whole period, but with spikes of rain in the middle. And whenever you had spikes of rain, you had recharging of the soil moisture, but it remains below 20% percentile, 20th percentile, then it is a severe drought. So you have spike, back, spike, and then it came out of it amelioration, as they say it. And the maximum temperatures, again, very few times below normal, but very many hot temperature days, which obviously will exacerbate soil moisture loss. And there's a kid shouting for her friend. He stands outside and keeps shouting her name. She has to come out, but hopefully that's not getting into the recording. The cloud cover for good measure, less clouds, but few clouds corresponding to rainy days. But you can see clouds don't necessarily mean rain. And wind speeds matter because you have very, lot of gusty wind days above normal, which can increase soil moisture loss, throw up dust as well, sensible heat loss, and so on and so forth, which exacerbates droughts as well. So that was a quick description of the figure, but it makes the points. So this period of rapid intensification satisfies the flash component of the flash drought, with soil moisture values falling below the 20th percentile, ensuring that drought had developed during the period of rapid intensification. So if soil moisture quickly drops to below 20th percentile, then that's rapid intensification. By July 2017, there are some details on what happened. The primary drivers associated with flash drought developments, including precipitation, temperature, cloud cover, and wind speeds, are shown as we just saw. This case study highlights the compounding effects of below average precipitation and enhanced evaporative demand that are important for the development of flash drought. So hot, dry atmosphere is very thirsty and evaporative demand goes up. Evapotranspiration begins to suffer, and if it grows fast, then the water use efficiency cannot respond as fast. So flash drought definition framework then, since the advent of the term flash drought in Peters and Svoboda, there has been both a strong desire to define the phenomenon and a lack of consensus on the proper definition. As Otkin et al. And Lisonby et al. Note, most flash drought definitions to date emphasize either the duration or the swiftness of onset and intensification. Even heat waves, we don't have a strong, agreed upon definition, but you have to be able to predict them, and often they are region specific, and often you have a good idea of where they occur repeatedly and so on, kind of a climatological map of hotspots. So define flash drought. This paper defines flash drought as a short-term yet severe drought events with a focus on both the event duration and severity. Emphasis on duration severity is adopted from a previous paper. Many of these definitions either include an explicit maximum duration criterion or formulated such that relatively short duration events 2 to 4 weeks are defined as flash droughts. Flash can mean appears and disappears, or also can grow rapidly, right? So concurrently, a lineage of studies emphasizes the rate of intensification for flash drought definition, largely beginning with these papers. These definitions include an explicit or implicit celerity or speed rate of growth criteria for drought onset and or intensification, such as a sufficiently large decline in soil moisture over a relatively short period of time. Again, what is a relatively short period? So always some subjectivity involved, but it's okay in terms of looking at impacts and being location specific in terms of the severity and the celerity and the definition and the predictions, right? So definitions of these terms, event duration and intensification, vary with perspective. For example, in the case of conventional drought, for a shareholder, the duration of a drought event may be defined as the period over which they feel impacts, whereas from a scientific perspective, it may be the period for which the anomaly of meteorological variable like precipitation or a response variable like soil moisture exceeds a given threshold. From either point of view, a conventional drought extends from drought onset to the end of the amelioration period, where soil moisture comes back to good levels, whether marked by the end of impacts or a return to mean hydrometeorological conditions. For flash droughts, however, these definitions are complicated because though rapid intensification is the key characteristic that disguises them from conventional droughts, flash droughts may also be the first phase of a long-term drought or a period of rapid intensification within an existing drought. Okay, here are some examples from country-specific studies and some global studies. Global studies tend to be coarse resolution, but even country studies can be coarse resolution, but depends on the data available and so on. There are also multi-country studies like continental Europe and Korean Peninsula, Southern Africa, multiple countries, and so on. Okay, I won't go into details here, but flash drought monitoring and indicators is very critical, because anytime you define something, if once flash drought is defined, people will go back in reanalysis and data to say how many flash droughts have happened, whether their duration, intensity, and frequency are increasing, and then you have to say what the impacts have been. So some retrospective processing happens of redefining some droughts as flash droughts and then making a history of the trends and changes, etc. Right? So drought may be defined as a sustained and impactful departure from the climatological balance of water supply to and water demand from the land surface. Flash drought adds to this a requirement of rapid intensification. So they look at basically precipitation deficit and high ET, evapotranspiration, and or evaporative demand. Okay, so skipping some details here, basically you have to have properly defined indicators, and from an operational monitoring perspective you need a suite of potentially effective flash drought indicators so that you have a complementary set of tools by which to inform flash drought response and management. Okay, so you have to be careful what we also mean by response. For example, if there is a prediction of a drought made and somebody qualifies it as a flash drought, either from the prediction itself or based on some local motivation, then demands for aid from the government can go up, crop insurance demands may go up, subsidized supply of other things may go up. So there is a human aspect involved in there. But anyway, the study proposes precipitation or reviews precipitation based indicators, evaporation and evaporative demand indicators, and soil moisture indicators, which is similar to other kind of events, chronic and acute stressors that we try to track, monitor, predict and look for change in the future. So you need to of course establish flash drought climatological characteristics. In flash drought climatology, a critical goal is to understand when and where flash droughts are most likely to occur. Quantifying the climatological characteristics of flash drought provides a foundation for improved monitoring and predictability through identification of seasonal and regional hotspots for flash drought development. Okay, so there have been many studies with different data sets, but typically you identify already known hotspots like Sahel and India, and flash drought frequency is generally highest in the middle of the warm season in equatorial latitudes. Rainy season, warm season and droughts can always go together, and they have spatial scales, so you can have wet regions and dry regions at the same time. A more prominent seasonal cycle of high flash drought occurrence in the warm season is evident in the mid latitudes due to elevated evaporative demand during summer. So Mahato and Mishra reported that significant warming and decline in precipitation resulted in an increased frequency of flash droughts in the major global croplands during 1981 to 2020. So that's a global study there, including looking at impacts on croplands. In addition, simultaneous occurrence of flash droughts in several major croplands across the globe has also increased during the same period. As I said, once you have a definition, you can retrospectively go and see how things have changed in the past. While global studies provide a high level summary of flash drought characteristics, further details can be gleaned from a regional analysis. Here we present a regional perspective of flash drought, focusing on continents and a subset of countries in which these droughts have been studied. The subsections are presented in alphabetical order, so you can go and read up those, very useful, but I am going to jump ahead and look at flash drought forecasting. Subseasonal to seasonal prediction. This is my favorite time scale as well, because 2100 projections are great. Decadal predictions would be really useful, and we have to understand what decisions can be made with 2100 projections and what the uncertainties are, even if you wanted to make decisions. But subseasonal to seasonal predictions directly apply to managing agriculture, water, energy, health, transportation, buildings, and so on and so forth. So skillful and reliable flash drought forecasts on subseasonal to seasonal timescales are essential for preparing for and mitigating flash drought impacts. Dynamical models have been used as a primary tool for this purpose, and there are some details on the timescales, lead times of 1 to 3 weeks, depending on the indicator, region, season, forecast model, and initial land state. So forecasts are initialized, so you need a lot of data to do that. The more the data, better your initial condition and likely the forecast as well. But these are very region specific. Some regions have a very high noise or internal variability, in which case prediction may be more difficult, and so on and so forth. But the interesting idea is that to improve flash drought forecast skills and complement dynamical forecasting systems, statistical and hybrid statistical dynamical prediction models have been developed. In these models, linear regression and More advanced nonlinear machine learning and deep learning methods were applied to account for the dependence of flash drought predictants on predictors drawing from observed current and past atmospheric and land surface states, S2S dynamical forecasts, subseasonal to seasonal dynamical forecasts, and potential sources of flash drought predictability, which can come from El Nino in a large scale background happening, or Madden-Julian oscillation, which can change the phases at intraseasonal time scales, and so on and so forth. This is important because even the global climate predictions or regional dynamical models can be at a few kilometer scale, and the information you need for impacts and ameliorating flash droughts have to be sometimes hyperlocal at farm scales, in which case you will need machine learning, deep learning for downscaling, and you will need data for doing that as well. Okay, so flash drought in a changing climate, which is what Mishra does a lot in terms of looking at the future. Analysis of both historical data and model projections globally and regionally largely find trends toward increasing flash drought frequency. These broader trends are attributed in part to anthropogenic climate change, as well as consistent projected increases in evaporative demand combined with variable but mostly small projected changes in global precipitation. Global precipitation is tricky because as you increase greenhouse gases trap more thermal energy, energy balance happens through global adjustment of radiative responses and precipitation evaporation responses. Globally, you can say something about these constraints and mostly small changes in global precipitation, but that can come with very large variances at small scales. Okay, so I think there is an example of Indian study here by Mishra that you can see that I have text, but I'm just jumping ahead because I want to keep this relatively short while giving you a good sense of the most important point. So the regional drivers of flash drought are important factors when determining regional prognosis of flash drought impacts with continued climate change. Beyond frequency of occurrence, studies have found observed and projected increase in flash drought severity, duration, and spatial extent in many regions. However, it's important to note that flash drought projections vary substantially across regions, models, and metrics, and these differences, placed in the context of future climate uncertainty, raise important questions to be addressed by further research, which we'll look at in a minute. So, what are the responses from rainfall to actual stream flows and other things, impacts? Among the most important confounding factors for accurate and actionable future flash drought information are the complex interactions between meteorological flash drought drivers and hydrological responses. Most studies characterizing potential future flash drought conditions do so using soil moisture, precipitation, evaporative demand, or evapotranspiration. However, the response of stream flow, groundwater, and reservoir storage to concurrent or compounding changes in precipitation and evaporative demand tend to be nonlinear and are themselves non-stationary. So the background state itself is changing because of chronic changes. You can think of flash drought as a acute change, right? These factors challenge our understanding of how projected changes in meteorological drought translate to changes in agricultural or hydrological drought and make it difficult to infer changes in one type of drought from projected changes in another. Okay, so what are the challenges for determining when, whom, and where flash drought impacts human communities? Okay, flash drought impacts. So this is a verb here. Empirical social science research on flash drought to date is limited and has primarily focused on US agricultural producers. US spends a lot of money on agricultural research, subsidies, protecting farmers, and providing predictions and monitoring and so on, even though Australia does much better in overall tools, interactive co-production of these tools and so on. Combining these studies with insights from the wider social science of conventional drought literature reveals that the same drought event will be experienced and likely to be perceived differently by individuals, households, firms, and communities depending on a range of social, economic, and institutional factors. In their typology of drought decision making, Cravens et al. Described the important relationship between the way a drought problem is framed, the way impacts or consequences are understood, and the preparedness or response options that might be selected. In the case of flash drought, one key question is whether those affected frame the drought event as flash drought or not. In some cases, conditions that satisfy the principles of flash drought, as we saw in a case study, may be perceived by those on the ground as substantially different from other drought events. In these cases, naming the event as flash drought may be useful. However, in other cases where an event satisfies the flash drought principles, those affected may understand the event as indistinguishable from a conventional drought event. Okay? In this situation, there may be less need, or it may even be confusing to focus on the flash drought nature of the event. An additional challenge is the diverse definition of flash drought definitions of flash drought exist among practitioners, complicating the ability to tease out whether perceptions or differing definitions are shaping the views on the ground. Okay? Of course, there are compound and cascading impacts of flash droughts. The rapid intensification of flash droughts can result in greater sensitivity and less adaptive capacity for response. In many cases, flash droughts are expected to have greater social and economic impacts than traditional droughts due to their rapid development. This can leave less time for communities to prepare. At the same time, the compounding climate impact drivers that can accompany reduced precipitation, such as extreme heat, high winds, may also result in more severe impacts that are harder to prepare for. Additionally, the rapid emergence of flash droughts and the difficulty of predicting them may add greater uncertainty to management efforts. For instance, in a study of municipal drought planning in California, Zaniolo et al. Found that preparing and responding to short, intense droughts was more challenging than milder, longer droughts because of the difficulty of coping with significant impacts in an accelerated time frame and with little lead time. We can try to go back and understand historic situations as well. If we look at Mayas, Incas, Mesopotamians, Mohenjo-daro, Harappa, greening of Africa, and all these instances in the past where we argue that civilizations disappeared, but anthropologists will say they don't necessarily disappear, they just move and merge with other populations and so on. We know that there were downturns in the monsoon, for example, or repeated El Niños caused reduced rainfall in South America, etc. But did they have long droughts with lots of flash droughts in the middle, and how these combinations would be less or more impactful on civilizations as a whole? So now we have a lot more data, satellites, and so many other platforms can monitor things, but it will be hard to go back and reinterpret those things because we don't have high resolution data. But this gives us an idea that now you have to look at chronic changes in some places like Sahel or dry parts of India and see how flash droughts are superposing on chronic droughts and how that may be making life worse. Okay. What are the future directions of research? It says future direction of research. Flash drought is a complex sub-seasonal phenomenon due to its drivers, development and impacts. While a rapid increase in research on the topic in recent years has addressed many key knowledge gaps, many critical research questions still remain. The basis of flash drought has been centralized on the three components of rapid onset, drought development and associated impacts. Due to complexity of the phenomenon, we suggest that the research community resist calls from practitioners for a strict comprehensive definition of flash drought. Instead, studies should use definitions that adhere to foundational principles relating to each component of the flash drought we saw. These studies specific definitions must balance their assessment of these components such that they remain sufficiently objective with regard to celerity and dryness and not overemphasize observations of impacts. You see the complication. Scientifically, we want to be very robust in terms of the processes of drought development, celerity and dryness, and then soil moisture, etc. may be easy to model and track and predict, but Once you start to look at impacts on crops, vegetation, and other impacts, then it becomes complicated. You want to map vulnerability, risk, exposure, and so on. Flash drought definitions that are based on observed impacts or subjective input risk over diagnosing flash droughts. Such definitions may miss the objective signals of a conventional drought onset and lead practitioners to identify what now appears as a rapid onset of impacts as a flash drought. This is especially the case if definition of flash drought relies on impacts or on monitors such as the US Drought Monitor, as in the operational definitions suggested by Pendergrass et al. That you can go and look at. So regional definitions will be helpful for regional predictions and responses and mitigating impacts, etc. But then comparing across different regions will become tricky because the definitions are not the same. So there is a solution aspect and there is a science aspect which have to be synergized. Finally, social science and impact focused analysis associated with flash drought development remains a critical focus area. While social science research is currently limited, there is an opportunity to better identify which impacts will become exacerbated with rapid onset droughts, which populations and regions might be most sensitive to flash drought development, and what mitigation strategies are most effective for addressing impacts. Key impacts of flash droughts are well documented as agricultural crop yield loss, ecosystem degradation, increasing wildfire risk, etc. But there is still a need to untangle the relationship between the timing of the development and cascading socioeconomic impacts. India gives a good example of this. I missed the Vimal Mishra paper that I wanted to mention, which basically looked at the flash droughts and their variability over India. Here it is. For example, Mishra et al. 2021 attributed the projected increased flash drought frequency in India to increased intra-seasonal variability of the monsoon with increased flash drought risk following failed or delayed monsoon onset. This is, obviously has to be put in the context of what has happened historically, because we have already seen some warming globally, even though India has not uniformly warmed, but the oceans around have warmed. That makes it more complicated. But Indian monsoon has a very fundamental intrinsic time scale, which is active break periods, which are intra-seasonal time scales, and even natural variability like El Nino, La Nina, Indian Ocean dipole, Atlantic Nino, etc. project onto active break periods in terms of their duration, intensity, and frequency. So it makes sense that future will continue to project on these time scales, and their variance will increase, and hence flash droughts will show it in their behavior. So you need to have some historical knowledge, dynamical understanding to make sure that future climate uncertainties are not taking you in a complete la-la land. Okay, so as I said, very brief. How long am I here? Oops, give me a second. Yeah, I'm about 33 minutes. As I said, it would be long. Typically, I try to keep for the podcast around 15-20 minutes, but instead of splitting into two, I did one. But you must read the paper and the references if you want to follow up. My camera is having some issue. I need to maybe get a new camera, but hopefully that's not distracting you here. Okay.